The Interested Reader podcast is about exploring the world beyond the textbook. We'll cover many lessons in math, physics, and astronomy, and then delve into the mysteries of the universe. Physics is fun, people just don't know it, and I want to change that. I want to spark your curiosity about the world around you and ignite your passion for exploring and questioning. I'm your host, Sarah Tyke. Come with me and let's take a random walk into the world reserved for the interested reader. Hi everyone, welcome to the Interested Reader podcast. Today we're going to be talking about the music of the spheres, and our mini lesson is going to be about triangles. So a few weeks ago, a fellow podcaster named Carolee Garrison was making a comment about how she had edited some background music for her podcast, and she'd removed something called the music of the sun rising, or something similar like that. And at first I thought that's kind of weird. Music of the sun, that's kind of strange. But then I remembered that there is this theory of music of the spheres, and I'd heard about it a long time ago. I haven't really thought much of it until now. So we'll get into that in a little bit. But first I want to talk about triangles. So just briefly, I think probably everyone is familiar with the Pythagorean theorem. So we're just going to go into a little bit about that. So we have our right triangle, which means it's a 90-degree angle. And then we have our sides here, A, B, and C. This would be angle B, angle A. So the Pythagorean theorem is that A squared plus B squared equals C squared. And then, of course, with triangles, we get all of our trigonometric functions, our sine, cosine, tangent. And I don't know how many of you remember or ever used the mnemonic SOHCAHTOA. That figured prominently into my trigonometry schooling. So if you don't know, we have SOHCAHTOA. So this means that the sine is the opposite side of the angle over the hypotenuse. The ka part, CAH, is the cosine, is equal to the adjacent side divided by the hypotenuse. And TOA is tangent, which is the opposite side of the angle divided by the adjacent side. So in our example above here, we'd have, say, the sine of angle B would be the opposite side divided by the hypotenuse. Cosine of angle B would be the adjacent side divided by the hypotenuse, and tangent is always just sine divided by cosine. Or you can do opposite to hypotenuse. So those are basic trigonometric functions. And just briefly, some of the easier, more useful numerical values here are things like the sine, if your angle is 0, is 0. The cosine of 0 is 1. So a 30, 60, 90 triangle is one of the most common, most useful, I think. So if you have a sine of 30, it's a half. Cosine of 30 is square root of 3 over 2. And these aren't, obviously you don't really need to know these, memorize them. I don't memorize them, I just look them up. There was a time when we had to memorize all of these. That was a long, long time ago. So these are just some basic ones, and sine and cosine are usually opposite each other. So when we get down to sine of 90 is 1, and cosine of 90 is 0. So those are the basic functions of, like I said, a 30, 60, 90 triangle, which, in case you're wondering what that is, it is simply a triangle that has a 90 degree, and then one angle is 30, and one is 60 degrees. So the Pythagorean theorem is very useful. That's one of our main equations of triangles. And one of the fundamental applications of triangles that I really like in physics was what we call a free body diagram. So anytime you have an object in physics, we always represent it as basically a point mass, a center of mass. And a common physics problem is sliding a box up and down an incline. So you'd have your incline here. It makes some angle, theta, with the ground. You'd have your box sitting on your incline. And then you start to apply all the different forces to it to figure out whatever you want to do, like how much force do you have to apply. So if we're trying to pull this box up an incline, this would be our applied force. So to do a free body diagram, that's your actual, this would be your setup. Your free body diagram basically boils this down into a point mass. So we would just basically say the center of mass would be like this black dot here, and all our forces are going to act on this black dot, which would be the center of mass of our box, our crate, whatever we're pulling up that incline. So you'd have a force acting directly downward here, which would be our gravitational force. So the force of gravity, which is also our weight, which is our mass times gravity. And then you would have a normal force perpendicular to your incline. And then you have basically a downhill or like a frictional force opposing you as you pull it up. Don't call it frictional force. So all of these forces will have various components to them. And those components you'll end up finding using trigonometry, using your angles. We haven't really talked about vectors yet, but for example, this gravitational force, as it acts downward, you're going to have, you set your XY coordinates so that this is your x-axis. And this is your y-axis. So this gravitational force now has a component acting along the y direction and a component acting along the x direction. So if we just focus on this triangle here for a gravitational force, what we have so this is our gravitational force. With its two components. A y component and an x component. So here's our 90-degree angle here. And in our diagram, we have our angle theta here. So in our free body diagram, this angle up here is also theta. So basically in this triangle, our gravitational force would be our hypotenuse. And then Fy would be our one side of the triangle, and Fx would be our other side of the triangle. So if we're trying to find our Fy component of this force, we see that that is the side adjacent to our angle theta. So if it's the adjacent side, that's going to be the cosine of that angle. So we're dealing with our cosine, which is adjacent to hypotenuse. So cosine of theta is the adjacent side, Fy. Sorry, this looks a little messy. Divided by the hypotenuse, which is our gravitational force, which is mg. So if we solve for Fy, we get mg times cosine theta. So mg is our gravitational force, and then the cosine of whatever that angle is, which again, in our setup, our angle is the angle between the ground and our incline. Okay, so similarly, so that's using our cosine angle. If we wanted to know the x component of this gravitational force, we see that the x component is opposite of theta. So opposite would be our sine. So sine of theta is going to be opposite over hypotenuse, so opposite is fx. Divided by the hypotenuse is mg. Solving for fx, mg times sine theta. So the whole reason you would be finding these x and y components of the force would be so that you can balance the forces, so that you can figure out what is the overall force needed to pull this. All right, I had a few technical difficulties there, and I kind of got cut off mid-sentence. What all I was saying was just that I like the free body diagrams for analyzing forces, and it's just a neat application of triangles. And we're going to see how triangles and Pythagoras figure into the topic of our podcast, which is the music of the spheres. So the music of the spheres is also known as musica universalis, or harmony of the spheres. And it actually dates back to the time of Pythagoras. He was the one who originated this idea. And he believed that the celestial spheres, the planets, the stars, anything up in the sky, produced a vibration that you would not be able to hear with your ears. He wasn't sure, I guess. But all of the celestial spheres must be vibrating, they must produce sounds, and they would all be working together in a harmony. And the first known use of the term musica universalis was used in 1609 by Johannes Kepler. And again, this was the philosophical concept that the movement of the celestial bodies would produce music in some form. Kepler was, I think, more about the movement, the rotation, the orbital mechanics of the planets making this music. Pythagoras seemed more to believe that the bodies themselves would emanate or produce a music. So we go back to ancient Greece here again, this time of Pythagoras, and Pythagoreanism. And so this goes back to about 600 to 500 BC. And Pythagoras is obviously most known for the Pythagorean theorem, as we just covered. But he was also the first to discover that music is mathematical, that there's actually a relationship between music and numbers. And he believed very strongly in the significance of numerology and that numbers essentially govern the universe. He believed that numbers exist outside of the human mind at the mystical interpretation of numbers and the roles they play. They actually govern the existence of life in the universe. And Pythagoras also came up with 3 of the 5 Platonic solids. So Platonic solids are objects that are 3-dimensional, and each face of the structure is identical in shape and size. So we have the tetrahedron, which has 4 faces, and that would be each face is a triangle. The cube of 6 faces. The octahedron has 8, dodecahedron has 12, and the icosahedron has 20. So the 3 that Pythagoras discovered are the tetrahedron, the cube, and the dodecahedron. He was also the first to study music mathematically. So he would measure the lengths of strings and quantify their relationship between the sound when they vibrated and the ratio, the length of the string, so the sound to the length of the string, and he would find these arithmetic ratios. And he discovered that the most harmonious musical intervals are the octave, the fifth, and the fourth. And these are all ratios of the first four natural numbers, 1 through 4. Now, I have no idea about music and music intervals. I have no idea. I've heard of the octave. There's supposed to be 8 notes apart, I believe. But fifth octave, or the fifth, the fourth, I don't know what any of that means. But Pythagoras discovered these relationships. And there's a concept called Pythagorean tuning, where you tune the frequency based on the ratio 3 to 2. This is known as a pure perfect fifth. Apparently, this is the easiest to tune by ear. Again, I don't know anything about it. Maybe if some of you out there are musicians or you know about music, you can drop me a line, drop a comment on the group page, and let me know about what this perfect fifth is. So we have, this will factor in a little bit later too. So we have the perfect fifth is a ratio of 3 to 2. And again, this is considered to be the most harmonious. It's the easiest to tune by ear. It's a pure perfect fifth. So Pythagoras believed that the essence of all things is numbers and that the universe is sustained by harmony. He and his followers often used music for health. They believed that medicine was to be used for the purification of the body, while music was for the purification of the soul. Now, one of his contemporaries, Aristotle, rejected this idea of music of the spheres because he believed that if the planets and stars made a sound, it would be so great that it would place a huge actual physical force on the human body on Earth. And since we just don't feel that, he didn't believe that it was actually happening. He agreed with the theory that it could happen, but not physically, not something that we would actually be hearing because we don't feel a physical effect. Now, here we come into the 1600s with Johannes Kepler. If you're a very famous astronomer, you'll know his third law of orbital dynamics, which we'll get to in a second. So in 1619, Kepler publishes a book called Harmonies Mundi, or Harmony of the Worlds. And here he details the theory that the motion of the 6 known planets could be described by musical intervals and harmonies. Now, he knew that these harmonies could not be heard by the ear, but he did believe that they could be heard by the soul, that they affect humans on a soul level, on a, it's a philosophical concept again. But he believed that these were very real effects that could be felt. So he postulated that the orbits of the planets and their distances from the sun are defined by these 5 platonic solids, and that the orbital motion, he found, almost perfectly matches musical harmonies. So he came up with 3 laws of orbital mechanics. The third law is the one that's most interesting here, and that is you take the ratio of the square of an object's orbital period with the cube of the semi-major axis of its orbit. And that ratio is a constant for all objects orbiting the same primary central object. So in our case, it'd be the sun. So what this looks like is you have, as objects orbit the sun, you have a centripetal force, and we're going to be equating that to a gravitational force. So the centripetal force is equal to the gravitational force. We're just going to start there. So the centripetal force would be written as the mass of your object, the planet little m, times its radius of its orbit. And we're going to go with an omega for its orbital acceleration. And then the gravitational force would be big G, which is the gravitational constant, times the mass of your planet, little m, times the mass of the sun, big M, divided by the radius of its orbit squared. So now we just make a few substitutions here. We're going to replace omega squared, or omega, with 2 pi divided by Capital T is the period of the object's orbit. And then you just kind of go through and start solving some of this, and we're going to reduce it down, and we'll do some gymnastics here. So I can skip over some of these steps here. What we're going to end up with is that we have t squared, which is the period of orbital motion, divide by r cubed, which is its radius of orbit, is equal to our gravitational constant times the mass of the sun divided by 4 pi squared. So this number here on the right side, that's all going to be a constant. The gravitational constant, the mass of the sun, those are going to be the same. 4 pi squared, obviously constant. So that is a constant. So what we have here, if you just invert it, you get the cube of the orbital radius divided by the square of the period of orbit and you can call this constant whatever you want. Okay, so here we have this ratio again of 3 to 2, which comes back to our perfect fifth of the ratio of 3 to 2. So when Kepler discovered this just confirmed to him that the planets indeed have music if they all have this ratio, this 3 to 2 ratio, which is a perfect harmony. So he also noted that when you do the ratio of the maximum and minimum orbital speeds, these ratios are almost perfectly equal to a constant musical interval, such as octaves and fifths. So you've got ratio of the radius to the period, you've got ratios of the maximum and minimum speeds, and Kepler was finding that all of these ratios mimic musical ratios. So he also liked to take these planetary motion equations and liken them to musical concepts. So we have these things called monophonic and polyphonic music. Again, I'm not a musician. This is all very new to me. So monophonic is a melody that has no accompanying harmony. So you basically have a single instrument or a single singer. And then you have polyphonic music that has 2 or more melodies. So you have multiple instruments, multiple singers. And Kepler compared the extreme speeds of planets with this idea of monophonic or polyphonic music. So if you have very high speed, you'd have basically a single note. It would just sound like a very high pitch. If you have very low speed, you might pick up more variation as a sound, as a vibration, because it's a little bit lower. He also looked at the orbits. If you have very eccentric orbit, it means you're very oblong, you're not a circle. You would have very great variation in speed. As you come very close to the sun, you would be speeding up. As you get far away from the sun, you slow down. If you have a very elliptical, eccentric orbit, you have these great variations in speed. So he thought that that would be like your polyphonic music. You have multiple speeds throughout your orbit. It's like having multiple singers or multiple instruments. If you have a low eccentric to your orbit, which means you're very close to being circular like the Earth, you basically have no variation in speed. So you'd only really have one note or one singer. That would be your monophonic music. So based on the ratios of the max and min speeds, Kepler likened the solar system to a musical arrangement, where he postulated, again, we only have 6 planets at the time. So Saturn and Jupiter would be bass, Mars would be a tenor, Venus and Earth would be altos, and Mercury would be a soprano. So this was all going on in the 1600s. It's all essentially theoretical. And we can't hear any of the stuff. They couldn't measure actual vibrations or sounds or anything of the planets. It was all based on orbital mechanics and equations and these ratios that they were all discovering. So fast forward to modern times, and we have essentially a modern take on musica universalis using orbital resonance. So here we look at how the bodies orbit each other, and if you're in resonance, the periods of these orbits are related by a ratio of integers, a lot like the musical notes we described, these perfect fifths, these ratios of 3 to 2. So for an example, Jupiter's moons, so if we take, they orbit, we have Ganymede as one of the moons, and you look at the ratio of their orbits, so Ganymede to Europa to Io, if you look at a ratio of all three of these, you have a ratio of 1 to 2 to 4. So for every one rotation that Ganymede makes around Jupiter, Europa's making 2 and Io is making 4. And one guy who's studying this is Dr. Matt Russo at the University of Toronto. And he has a website called system-sounds.com. And he and his colleagues measure the vibrations, the music of these planets, essentially. And one of the ones that they have come up with that they study is called TRAPPIST-1. And it's a planetary system that they have put music to. So if you go to their website, you can click on it. I've got the YouTube thing here pulled up. So just reading a little bit from their description, what they have done is they've assigned a piano note every time a planet passes in front of the parent star, which we call a transit. And they've assigned a drum to every time a faster inner planet overtakes the slower outer planet, which is known as a conjunction. Now, they can measure these pitches with actual instruments, but they're way, way, way below human hearing. So in order to produce these sounds, Russo and his team have had to scale up these orbital frequency by 212 million times to get them into a range that the human ear could hear. So this is what it sounds like. So this is the first planet orbiting the sun. Every time it makes an orbit here, you hear a ding. And then they add in a second one. So every element, every new note you're hearing is a new part of the planet system that they're adding in. So I found that to be very cool. And at the end, let's see, I'm just reading from their description here. So they say the TRAPPIST-1 system is a resonant chain, which means the periods of the planet's orbits are very close to whole integers. So these are the 3 to 2, the 4 to 3, what we just discussed with Jupiter, the 1 to 2 to 4. So they're all very close to real whole integers. And another thing that they do, which I love, so that's using your orbital resonance to kind of create, again, this music of the spheres. Obviously, they don't sound like this because these are pianos and drums and snares, but they're using real data to come up with these sounds. So this is a very, I think, a beautiful representation of what is actually out there. Something else they do is this black hole. Now, this is something that they've actually detected. So there are, again, this is just reading right from their website. Sound waves were detected in X-ray images in this Perseus cluster where this black hole is located. And the pitch of these sound waves, again, I don't know music, but is a BB, 57 octaves below middle C. This is the lowest frequency of sound waves ever discovered. So they had to raise the sound collected by this instrument. They had to raise them by 57 to 58 octaves so that humans could hear it. And this is what it sounds like. I hope you enjoyed this episode. I just want to say in closing that I really enjoy this topic about the music of the spheres. And while we can't physically hear the planets and the stars, I do believe that they are creating some sort of resonance. Somehow they do affect life here on Earth. And I'm going to continue this topic into the next episode as well. So we'll talk more about the modern aspect of this and just some of the instruments that they've been using to collect data, some more of the sounds that we've heard from the sun, the stars, just get a little bit more in depth into the modern take on the music of the spheres. Hope to see you then. Thanks, guys. Bye. I hope you enjoyed this episode and are inspired to question and investigate the world around you. Let me know what you're thinking about. You can contact me through the website, theinterestedreader.com, send me an email at sarah@theinterestedreader.com, or join the Interested Reader group on Facebook. I'll see you at some later time T, where T is greater than T naught, and T naught is equal to now. Thanks for being an interested reader, and I'll see you next time.